Hi guys. So I have this video that I put together of a recording that I made in 2016 of me teaching some high schoolers a class when they were visiting University of Illinois. Now the class was written by me. It's called Models of Computation, and there's three models that I essentially cover. The first one is the Turing Machine model / finite state automata. The second one is formal grammars, and the third one is cellular automata. And then for each one of those, I basically have 4 slides. The first one is a slide that is a challenge. It's a mechanical puzzle that introduces you to the model. The second one is where I give you content, tell you about the model itself. The third and fourth are basically a creative challenge and a possible solution to it, essentially. So the class itself, the way it was presented, probably wasn't very impressive. Same with the way it was recorded. But the content of the class I find very interesting and would love to expand on it and maybe even make something online to help teach these concepts. So I hope you guys enjoy watching the video, and I'll see you guys later. Bye.
So how'd you guys hear about the sale in the first place?
I just got an email on my
I signed up for the last year's contract.
Are you guys all still in high school?
Yeah.
And it was just an email, it wasn't like your high school rep like told you about it or anything? Okay, yeah. I don't really know much about it either myself because I actually haven't been here for the morning part of the day, so. Anyway. Here we go. So try to just stack your papers, and from now on just look at like the first ones, because I'm gonna have you guys do some puzzles. And I'm gonna be right back. You guys all have pens and pencils? I don't have.
yeah.
Because somebody's gonna provide them. Let's see. It should be here soon. But I'll be right back. I'm gonna see about that.
Sure, I was down the wrong hallway. Oh, I meant.
Sorry.
Are you a high school senior?
No, I'm software.
Okay.
How about you?
I'm a senior, yeah. I thought this was like just for seniors, but I guess not.
I guess we're like 7th graders.
Okay. How old are you guys?
I'm a senior.
Okay, senior. Sophomore and senior. Are you all doing it? Are you
Okay, she promised me she was on her way with some pens and pencils, so. I have one pen. If someone wants to use it right now.
I'll take it.
Okay. Okay. So this class is called Models of Computation. How many of you guys think you have an idea of what that means? Or what do you think it means, I guess, would be the best question. You.
Using data structures in order to figure out the most efficient way of doing something.
Okay, data structure is efficient way of doing something. What were you thinking?
just like on a more like chip level how computers work.
Okay, how computers work on kind of on a chip level. So computational equivalency is something that's it actually originated from the math field, and it was actually just kind of a definition of what computation is, just mathematically. So anyway, how you guys doing?
Pretty good.
So I'm not sure when we'll get our pens and pencils and stuff, but I want to start off each kind of section with a puzzle. So the first thing we're going to do is kind of like it's just a puzzle, and then we'll go in depth into it later. So different caps. The first one's going to be just your puzzle thinking cap, I guess. I'm going to figure out how to do this puzzle. And then after that, we'll have listening, and I'll show you some stuff, so watching. And then I'll give you a challenge for creativity, so you can try to, instead of just following directions, you're actually going to think how to solve something. So it's almost 1 o'clock. Do you guys have a good day so far? Yeah? What kind of stuff did you see in your classes? Was it fun?
Yeah.
Fun stuff? When I looked through all the titles, I was like, wow, mine looks like it has like the most boring title out of like all of them. Like the other ones like, oh, Minecraft and program stuff in Python and stuff.
Next year.
Okay, it's 1 o'clock, so I'm gonna get started. Even without our, I guess try to imagine it. I guess you don't really need to write too much for this first one, so I'm kind of lucky. So the way this works is, this is our machine puzzle here. And what you're gonna do is, you're going to kind of start where this box is pointing at, and that's kind of like your cursor. It's like that little box is you're choosing to kind of start there. Now, if you know what this is, don't just blab it out loud, but we'll get into that later. But right now, you just kind of start right here at this box, and then you're also going to start here at the same time, and you're going to look at both this section up here and this graph right here. It's called a graph. And you're going to follow these instructions that the graph tells you. It'll tell you exactly what to do with the boxes. So when you start here and you read the box, this first character is going to represent what you read. So if you see an X there, you're going to do this. You're going to follow this path. If you see an O, you're going to follow this path. And then you're going to do these two instructions right here. The second one is what you're going to write as the new block value right there, where you're at. And then after you write that new value, you cross out the old one, you write the new one, then you take whatever path that this says. So when it says right, that means you're going to move right to the next block. And then the arrow, of course, tells you which state you're going to be at. Does everyone understand that? Any questions?
The change of state, like, do you mean like do you move on to the next?
Yeah, so like for example, I'll just show you how we do the first iteration. So we'll start at that box, and I'm at A, and so I check these three paths, and I look at this one and I say this is the one that matches. So I take this path, and since it points back to itself, I'm going to be back again here. And I'm going to cross that O off and just write an O again, but I'm going to move that arrow to the right, and I'm just going to repeat the process, starting from where I left off. Does that make sense?
Yeah.
Okay, go ahead. Does everyone have the 3 sheets?
Does anyone have writing utensils? Does anyone need writing utensils?
Yeah.
Perfect, okay. I'm pen or pencils.
It should work, I think.
One of my colors.
Wait, so the direction it says,
Anyone
that
else?
indicates like what
Thank you
part
very
you're reading the script in?
Yeah, so the direction here is going to tell you which way you're going to move that arrow right there.
Okay.
You're either going to move right or left.
No, it's good.
Yeah.
everyone to get pens too? They work? Cool.
Thank you so much.
No problem.
Oh yeah, and I forgot to mention, if you make any mistakes, it will probably end, it might end really badly because it's hard to go back and you, I guess, have to redo a lot of stuff if you ever make a mistake, so. But that's okay, if you make a mistake, I'm not gonna, you're not being graded or anything. Is anybody almost done? Yeah?
At the end, do you go back to the start or just stop?
Once you reach end, you just stop completely. And then, so did you finish? So do you wanna, so do you wanna share what you got? What your, I guess what your strip now says at the top?
Alright. X, 0, 0, 0, 0, 0, 0, 0, X, X.
Okay. So how many zeros are there?
7 zeros.
And does anybody want to like solve the riddle of what we just kind of did here? What you think this kind of? Well, I called you last time. Were you using your head? Okay, go ahead.
Move the plus.
Okay, we moved the plus. Yep, we basically moved the plus. Oh, but the plus isn't there anymore, right? You got x's. So what does plus usually mean? Add, right? Yeah, so pretty much added 3 and 4. It's a very simple, what we call an algorithm, but that's basically what this does is no matter how many O's we have here and how many O's we have here, I think given at least there's at least 1 on each side, it'll add them and then we'll have 7. So if we follow the state machine at the bottom, you'll notice that we just keep moving this thing to the right and replacing them all with O's. And then we reach a point where we're doing something different, but we're pretty much doing the same thing, but we're in a different part of the state machine. And once we reach there, we don't check for pluses anymore. And we just go there. So it's basically an adder. So anyone know what kind of machine, what this is called? Turing machine, yeah. So Turing machines are a really, does anyone know why it's called a Turing machine?
Alan Turing.
Yeah, Alan Turing, yeah. He came up with this model and was working on this stuff in the 30s and the 40s. And it basically says that, well, we have a very large tape. We'll just assume that it's unbounded in length. It can be as long as we need it to be. So if we tried to describe its length, we would just say that it's infinite. And then we have a state machine that's finite. We have a small machine here that will process some kind of computation on that part of the tape, and then it'll decide whether it wants to move right or left on the tape. Now there's different forms of this kind of machine. Like for example, instead of thinking of it as a tape, you can think of it as what's called a stack. and your computer kind of works like this. It uses stacks, which basically you start with, I guess if you want to start with an empty stack, you can just place items or information kind of on the stack, and then whatever you see last that was on there, that's the next thing you retrieve out. How many stacks do you think it takes to make a computer that can kind of work with any algorithm possible? Given that the rest of your computer is just finite, but your stacks are unbounded. Anybody have a guess? It's 2. So it's kind of like you can think of this tape as you can go back and forth in 2 directions. If you just have one stack, you're actually limited. You can't compute everything else. But as soon as you have 2 stacks, you can compute the same things that you can compute with 3 or 4 or 5 or 1,000, because it's just as powerful. It might be really slow, or depending on what your system is, but mathematically it can simulate whatever. Think of a game you want to play or something like that. You would just have to decode it, but it can compute that. It can do square roots and things like that. So, yeah. So Turing machines kind of are a little slow, and I don't know, it's kind of boring to just do it by hand, right? Kind of crossing off numbers and stuff like that. So I want to show you guys something a little more fun. So I just called this Fun Turing Machines. So this right here, that's a lot of pixels right there. And I just want to show you where I got this. I took this clip, and hopefully my internet works right now. So, trying to click on this. Uh-oh. I should have tested this on this. I can't click slower, and that's very sad, because then I could show you what's going on, but I can't click slower now. Fork me on GitHub. Maybe if I change my screen size, it won't mess it up. Or maybe if I try, let's see here, Firefox might work, possibly. I don't know. Oh, I can click faster. That works. Oh, now it's stuck very fast. Anyway, when you slow it down, you'll actually just see one kind of pixel moving around, and what it's doing is, please work. Okay, I can't slow it down, so it's kind of sad, and I also can't click random. You know what? Here, I saved another link though. Here's another one. So if you click random, you'll see just like different things generating. Sometimes you'll see like a, I don't know how to explain it. Sometimes you'll see something that keeps moving, and sometimes you'll see something that just stays static, because it's like that, for example. Here we go. Okay, so if I keep refreshing this, I can show you different ones. So this one just stays all red. And what's going on is, you'll see there's a number of states is 4 and number of symbols is 3. If I increase the number of symbols, that's the number of colors that we're using. Sorry guys. If you have a computer, you might want to like Google this sometime. It's just Google, I guess, Turing Drawings. It's really cool. And play with that. But when you slow it down, basically what you'll see is just kind of this little guy who moves around. And what he's doing is he's kind of deciding, like, he has his own little state machine that he's following. And the number of circles you see is that first number of states. And they're all connected to each other, and they're kind of deciding, they're just random. Like this, it's kind of random. If it sees like the color black here, it might say like, okay, when I see black, I'll just stay in the same state. Or it might randomly like have a one where if it sees black, it'll go to that state instead. And so what it does is these tell it what color to draw next and then which way to like turn, which way to go. And so it's basically, instead of using one of these flat strips, it's just working like on a 2D plane. Anyway, it's just a fun tool. And yeah. It's supposed to only take up 5 minutes of the class time, so. Wish I could show you more of it, but I can't click the GitHub thing, or can't click it with the GitHub thing. Okay, so we'll probably need more time anyway because the next thing is kind of challenging. So here's where your guys' creativity kind of comes in. Based on what you've learned, I want you to try to do something kind of creative. It should be pretty simple. It should be pretty easy. But based on how many O's we have here, I want you to have the arrow pointing to an X or an O, depending on whether there's an odd number of O's or an even number. So if it's odd, I want it pointing to an O at the end. And if it's even, I want it pointing to an X. Okay? You guys think you can do that? And by the way, this one's 0, so it's even, in case you were wondering. So that's kind of why evens should be pointing to an X, because there's no O's to, unless you, well, I guess you could place an O, but I don't want the number of O's and X's to change, I guess. But that doesn't really matter. As long as you end on the right character, then we'll consider that a correct answer. Do you need a sheet?
What? No, I'm good.
Okay. Yep. X's, it should end, your arrow should end on an X if there's even, and an O if it's odd. That's really all that matters. Even if you mess up like the whole line, which you probably don't need to, but. Yeah, okay, so if it starts off, so for example, this one right here should end on an X. The arrow should end on an X. Whatever your state machine does, the arrow should end on an X because there's an even number of O's. So in this one, since there's an odd number of O's, it should end pointing at an O to say that there was an odd number. It's basically like a machine that's telling you how many O's, or whether the O's were odd or even.
Could we create like an or type of thing, like even or odd?
Do you mean, what do you mean by that?
Like, how can we say like if the amount of O's is odd, then do this. If the amount of O's is even,
Oh yeah, okay. So your choice. So basically, what you're gonna do So I'll kind of give you a hint on how, like, because what I'm allowed to do is just write a state machine that basically, it's allowed to move right or left. And I'll let you guys also choose to stay, which means don't move right or left, just stay where you're at, because it doesn't really matter if you have that or not. It's just easier. Anyway, so just to answer your question, so if I'm going to start here, I kind of need to, I don't have a lot of memory in my state machine, so I can't remember a lot of things. But this remembers everything for me. So this just kind of remembers what I need to remember to think. But this kind of remembers kind of like how a book remembers. It can store as much as I want. The state machine only remembers what I need to know at the current time to kind of mess with this. And so the idea is odd or even can be extremely long, it can be millions. And so how with just a few states can you determine, just by going left and right from one to another, whether it's odd or even. And so what you're going to end up with is you're going to somehow at the end, maybe you'll be at like an O or an X, and depending on what state you were in, like you might have a state that you can just name even or one that you name odd, and it just kind of switches back and forth or something. It'll kind of end up telling you where you're going to end. So it's a little bit of a hint there, but does it make sense?
Yeah.
Okay, so it's already 1:20, so we're about 1/3 way done with the class. So we're gonna go ahead and move on. How many of you guys think you got an answer? Do you want to put it on the board, or what do you think?
Sure.
Since did you already answer one, or you already answered the first one, right? You want to go ahead and do it then?
Sure.
Sorry, didn't mean to. Trying to. As many
Could I
people.
sort of build off of this?
Yeah. You can go ahead and use whatever.
Yeah. So I think it's.
You can erase anytime. Nice. I think that should be right. In fact, I think that's the same as mine. So, yeah, I sort of cheated with the state thing, but yeah.
It should not be he says O, right? Or even to, or odd to even.
Well, wouldn't it just?
Yeah, it seems like it would
Shouldn't
be
it-
forever had left.
Yeah, shouldn't it be right?
I think. See, what's going to happen is,
It should be moving.
as soon as it gets to the end, we finish.
Yeah.
So basically, what's going to happen is, depending on whether we're odd or even, as soon as we get to the end, either we're going to stay at the X
Yeah.
or we're going to move left. Right?
Well, okay, but the left pointing from odd to even, it says left. And it seems like it should say right, because otherwise it'll just sort of oscillate between the two.
Oh, that's my mistake. Wow, I thought I made these correctly, but apparently I made sure to check. I guess the things that when I give you the information that you have to solve the problem, like that's really important to be correct. But the solution, yeah, I made a mistake. You're right. It is. You move right each time. That's good. Thanks for catching that. So yours is, I think, the correct one here.
Wait, so what do the two symbols represent?
The two?
Yeah, like the formula direction.
Okay, so the first one is telling you, once you're on a state, this first symbol basically just tells you which arrow you're going to choose. So if it's an O, you'll choose this arrow. If it's an X, you choose this arrow.
Okay, and the second?
And then the second number is the one that you're going to write to that spot. So if there's an X here, so right here, we're just writing the same thing as we're seeing, so we're not actually changing the states. But basically it means like, oh, if you're at an O and you're going to move, if we're going to do this one, then we're going to rewrite it with the new O. That's all it means. So, yep. So we'll go ahead and think about, I guess later on we can think about different things that we can make with those, with these Turing machines. This is called a finite state machine, and then a Turing machine is when you use your tape to go with it. And now we're a little behind schedule. And this puzzle is kind of tricky. This puzzle is basically just do exactly, so we're back at just kind of I guess the doing path. You're not going to be creative, you're just going to kind of follow exactly the instructions. So in this case, go ahead and we're switching gears here, and we're gonna draw two trees for each of these things. Each of these, they're called, well, maybe I shouldn't tell you what they're called yet, because it's kind of a surprise. But basically the way this works is you have this starting capital letter, and then you have an arrow. And then what the arrow means is everything on the right of the arrow is what you're going to replace this with. But everything, the bars mean that you have a choice. So you can just randomly choose either this left side or the right side, it doesn't matter. But I want you guys to make two different trees. They have to be different in some way. Two different trees of these first two. And here, this one's just an example. So if you start with A, well, I could replace it with just A, lowercase, or I could replace it with two uppercase A's here. And both of those are now considered just next to each other, concatenated, like a word basically. Think of it like a word. And now I go through each of those letters and replace each of the letters in that word with something. So I decided to replace each of those with lowercase a's. Does that make sense? This one's got a lot of stuff. So for the ifs and the elses and everything like that, don't worry about what all these little letters are. Just worry about the capitals. Because the capital is what you replace with stuff. So that big S, you're going to replace with either this thing right here, or this thing, or that little s. And so if you don't replace it with a little s, it'll just keep going on forever.
What's the difference between like AA and the example one and like A plus A?
So for this, it doesn't really mean anything, except that if you were to write it all left or right, you would have pluses and spaces in between the A's. But you can write this from left to right pretty much. Like I could write, like if I wanted to describe this, I could write like AA. Well, that doesn't fully describe it, but we'll get to that. And then if you can, I want you guys to write two trees for these that when you write them at the bottom from left to right, they're the same, but the trees are different. Do you get what I'm saying? But that might be a little tricky, so. Yep. That would be an example of this bottom one. It's good. In fact, do you want to share that on the board? I like that one. Just what you drew is really good. So he actually messed with the example a little bit and kind of did that challenge with the example one. It's a little easier, I guess. And then you drew another one too, right?
Yeah.
So, yeah. Sorry. It's kind of a point to this. Anyway. But yeah, you guys can keep going and we'll look at this solution in a second. Did anyone get the first one? Two different trees for the same string at the bottom. For the second one, maybe if we work as a, thinking maybe we could work like as a team a little bit. Who knows? So, what if we had something like this? Do you think there's two trees for that first one for this? I know the rules, part of the reason for this puzzle is to just kind of introduce you to how this works. So if you didn't really understand what's going on, well, that's actually the point of the puzzle, is to try to get you to like realize, oh, so this is just how it works. But check this out. And then in between here, these pluses, they count as part of the thing. The only thing that doesn't count as part of the end string, and I probably should have made this more clear, is the capitals. So, anyway, I just kind of drew it out there. But that's kind of a drawing that I found online. Another way you can draw it. Does everyone kind of understand how that works? So do you guys think we can figure out the other one? What do you think? This is the else one? You know what this is called?
Binary.
It's called, so that line up there is called an ambiguous grammar. It's called a formal grammar that can be written, that can basically, there's essentially two parse trees for a string. If that makes sense. So anyway, what do you guys think? Do you think we can see if that second one is ambiguous by drawing two trees? How do you think we do it? Let's not draw it, let's just talk about it. How do you think we do it? You can replace these capital S's with this S again, right?
Yeah.
So imagine you have something that says if then else, or if then and then if then else, right? So if you have an if then here, how do you know which S that else belongs to? Is there a way to figure that out? Or is it impossible? Can there be two of them? You guys want to see the solution? Is that okay? Were you onto something there? What's the C's? Oh, I see. Okay. Yeah. That's the solution that I kind of drew up here. And this line right here, this is the string. It says if C, then S, else S. And I probably didn't make that clear enough how that worked, but it basically includes everything except the capital. Pretty much everything at the bottom. So if it's capital, it's not really at the bottom because you replace it with something. You get that? Does that kind of make sense? It's kind of tricky. It's kind of tricky. It's a lot of information in a short amount of time. But yeah, formal grammars are a very interesting thing, and you can do a lot of cool stuff with these. And I guess the most interesting part is that there's actually a classification for them called the Chomsky hierarchy. And you guys might want to write this down because I don't actually have slides on it, but if you want to look up something that's really interesting, Chomsky hierarchy. Has anyone heard of Chomsky hierarchy before? Maybe? I think there's some cool like YouTube videos on it and stuff. Basically, there's a classification between grammars, like this here at the top, and state machines. And the way it works is, if you have just a state machine with no stack, with no tape, you can prove, or it's easy to prove actually, that is equivalent to what's called a regular grammar. And a regular grammar, I wasn't really planning on talking about this so much, but it's really interesting. It really relates because it kind of shows how computation can be viewed in different ways. And it's very important to see these different ways. And they're actually really useful. So you have a real concatenation. So if you have like A, A or something like that, those are concatenated together. You can describe these grammars by putting like two things together, and you can just say like A star B, for example. And star is a different thing. Basically, what it means is any number of A's including 0. So what this means right here is this means the set of all strings such that it has this pattern. So it's just the string B, or the string AB, or A, And since it's using concatenation and the star, and there's one other thing you can use. So you can say like or C. Everything you can represent in a finite state machine can be represented here by these rules, and everything that you can represent with these rules can be represented with the finite state machine. So they're actually equivalent. Neither one can do anything that the other one can't do. So, and as soon as you add a stack, you have what's called a context-free grammar, which is what I was showing you guys, where you have a capital letter on the left, but that's the restriction. But there's also something called an unrestricted grammar, where you don't just have capital letters on the left. And I'll get to that in a second, but before I get to that slide, well, we'll go to that slide first. So here's an example of something that generates a composite number of A's as strings. It looks kind of complicated, doesn't it? And it's also kind of going off the screen, but actually that's the last line. The last line is HX lambda. So if you just kind of expanded this grammar randomly until you got all little a's, the only thing you would get is some string of length that's not prime. Does that make sense? So it doesn't really seem that useful, right? Like, who would just come up with something like this? Like, why wouldn't I just write some computer code or something like that? So actually, The reason why it's good to understand these things and understand these models of computation is because they're actually really useful for abstraction. So when you write a programming language or you design an algorithm or software, and it's even kind of hard, even I think for even computer scientists to come across this, because this particular one is more of a mathematical view instead of like a machine view. So there's been difficulties with it in the past. How many of you guys have heard of the programming language Haskell? Yeah? What do you guys think of that? Have you heard anything about it? Some people say it's not really useful, or it's not really, like, how do we use this? But they've learned how to use I/O monads to use inputs and outputs with the language, and it turns out, from stuff that I've been personally researching, that the language is more, that particular language is better suited to kind of explain how to organize the code, like the structure of the logic of what's going on, rather than exactly what the machine is doing, because there's issues with state. Because it's so pure in the way it works, is that you can't mess with state, and so that makes it actually difficult to work with inputs and outputs. But it turns out you can actually use inputs and outputs with languages. So do you guys think Turing was the first? How many of you guys think Turing was like the first guy to come up with the model for computers? Does anybody know who his advisor was at Princeton University? Who came before Turing? Who was his professor? It was Alonzo Church, and he came up with this model that so many people didn't even understand, and it was called lambda calculus. And I should actually show you guys this because it's so cool. This model is proven, and I'll just show you guys the wiki because there's nothing really pretty about, like, there's nothing really like visual about it, I guess. But I guess I guess I could just stick with what I had for you. But okay, here. Well, I'll just show you guys this. So he basically proved that you could do these different types of computations, like add numbers and do, for example, like here we have like this multiply function. It looks kind of weird, and it's like, what is that doing? Well, what it's doing is it's actually taking these functions and these abstractions, and those are like the only things that exist in this grammar. So everything you're looking at, it's like, oh, that's a function. Oh, that's an abstraction. So that's it. Like, that's all it is. But he represents numbers with them. For example, he says, right here, the number 0, it says lambda f, which means a function that takes in x and then just gives you back x. It's like, wait, how is that 0? But then when he says, describes what a 1 is, he says fx right there. And then he keeps iterating, and then he comes up with these other functions that turn out to add and subtract and do things like that. And this is actually the calculus, or the grammar, that Haskell kind of gets its lambda from. And so our language research and a lot of stuff with software nowadays actually just takes its ideas from this, because it's such a simple model. It's so specific. It's so low level. And it's Turing complete. That's the thing. It's equivalent to the Turing machine. So what happened was Alonzo Church came up with this model. People didn't really understand what was going on. He's like, oh, you can do all of math with this. And they're like, what? We don't believe you. Alan Turing shows this machine. They prove that they're the same because it's actually pretty simple to do that. So he proves, well, I'm not sure exactly how simple it's but it was simple enough where he was able to come up with the proof and show that the Turing machine was equivalent to that. And when people look at the Turing machine, they think, oh, well, there's nothing really extra we can add on as a machine, as a mechanist. I think this is as powerful as you can get, because it was easy to show that a Turing machine is equivalent to like a Turing machine with as many tapes as you wanted and as many heads as you wanted and things like that. So this I would describe as a really it's kind of difficult to come up with really cool things for it, challenges and stuff. So I kind of just stuck with grammars because it's kind of confusing, I guess, and it would take a while to kind of get it. But there's a startup incubator called Y Combinator, and it's named after this Y Combinator, which what it does is it basically just replicates what's there, and that's what allows it to be Turing complete. So let's go ahead and get back to the slides. It's running out of time here. So I don't know if you guys want to try this. Maybe we could, how many of you guys think you want to just try this one at home? Because we're kind of short on time. I'm going to go on to the next topic. But basically it says, this is an ambiguous grammar, and it says make an unambiguous version of it. So the solutions are in the next slide. We won't worry about doing it because we already talked about all that stuff. So we're just going to skip to the next section, and we have one more puzzle because I really think you guys are going to like this one the best. This one will wake you guys back up because it's more visually interesting. We just got through the boring section. So this is a puzzle right here. I don't even need to touch the board for this one. For this first row up here, I want you guys to look at every 3 blocks. For example, these 3, and these 3, and these 3, like all the way down. And for every 3, copy kind of what this tells you to do. So if there's a white block, right here, white block, go ahead and put a block right there in the middle. And keep doing that 1 row at a time until all the rows are full. And just assume everything off the edge is just white. Oh yeah, and if you're starting to get sleepy or you yawned in the last 5 minutes, go ahead and just get up and down a couple times. Because we're past the grammar stuff. And I didn't know how to make that fun, so anyway. Oh, and don't peek at the solution either. I added in the solutions to the slides so that when you guys take it home, you can look through them, check your work and stuff. And we'll see who can get done first, to the point where you can't do it anymore.
But I did it like I didn't start initially like that.
Oh, you did it earlier?
So
Okay.
that's the
Okay.
thing.
Do you mind if I look at it?
Yeah,
Cool. And you already checked it with the solution?
I was just applying the.
Nice. Something of justice?
Yeah.
Is that? I haven't heard of that. Oh yeah, we're assuming those are white. So we're copying. You know, I might have. Let's see. I might have screwed that one up actually.
Well, it does end in these model statements, statements either.
Yeah, let's see here. What was I thinking? Okay, you know what? I should tell you guys a secret. I was up a little late last night, and then I had to get up at like 5:30 in the morning. And I was making these slides, so I was hoping I didn't leave any mistakes, but I was kind of trying to keep myself awake too. But yeah, I have been planning this class out for a while. I just hadn't had the materials kind of, anyway. But yeah, I think he's got a what? We might just say that row down, just ignore the solution then. Maybe just mark it off, because I think you're right. I think I screwed that one up.
Also,
Maybe. Is it wrong? Is it?
it goes off the edge a little bit, includes 1, 2, 3.
The second box in, the row above it, if it's black, white, white, then that middle one should be black, right? So I think I...
No, the middle one would contrast, this statement would apply with these two boxes.
No, I mean the second one underneath that row.
Oh, yes.
Yeah. So yeah, go ahead and just ignore the solution. Where I stopped the solution, it actually doesn't stop. So yeah, I kind of screwed that one up. Just go ahead and like X it off. Thanks for catching that, by the way. Appreciate it. So yeah. So what do you guys think this is called? Have you heard of it? Sierpinski triangle, yeah. So it kind of looks like one, but like, are you sure it's Sierpinski triangle? What happens if we keep going? Well, that's what happens if you keep going. So that one should be correct, because that one I just got on I think a computer generated that one. So. Yeah. So it's just like an infinite fractal right there, right? So what you guys just learned was something called Rule 90. This is called Rule 90. So actually Wolfram, do you guys know about Wolfram, like Wolfram Alpha?
Yeah.
Stuff like that, yeah. He came up with, he was studying this kind of stuff, and he came up with this is actually called the Cellular Automata. And Rule 90 basically is, given these sets of 3 colors, it's these 8 colors, that's all it is. So if you take that binary, those 8 bits, and you just give it a number, it's the number 90. And if you use the number 110, it's Turing complete. You can actually do computations. You can do square roots, you can simulate Minecraft, you can do like anything with a one-dimensional line using Rule 110. Now you'd have to encode and decode in order to get like see if you wanted to see cool pixels or something, but it can do any algorithm is the point. There's another picture of a cellular automata. And what was the name of the one that you said earlier? You said you heard of what's your name in the back? Yeah.
Riley?
Carly?
Riley?
Riley? What
Yeah.
was the thing that you mentioned earlier? He said something. There's a 2-dimensional version of this. Does anybody? Conway's Game of Life, yeah.
Oh, right, that. Yeah, it's later.
Conway's Game of Life. So this is a 2-dimensional version. The rules are a little bit different. They basically have to do with how many neighbors a cell has. What do you guys think that this right here is? Yeah, it's a computer, isn't it? This is a Turing machine. In fact, this is a universal Turing machine. Do you know what that is?
It creates another Turing machine.
It's a Turing machine that has enough power in it to where to where the finite state machine is basically designed in such a way that, yeah, you can basically just emulate anything that you want just by giving it the right step, by giving it the right information. So this is like its tape right here. Look, this is this left and right stack. That's its tape, and here's the finite state machine. And it's a universal Turing machine. So yeah, it can emulate anything you want. And yeah, it's in Conway's Game of Life. Did you guys ever see that before? I want to show you guys some video. How many of you guys have not seen a video of Conway's Game of Life? 3, 4. Do you guys want to? Okay. Probably sick of me talking. I don't know. Here, I'm clicking on. So I have a whole bunch of videos about links, like 3 links for this thing. This thing is so cool, and yet with this one, I don't really know. Me as a computer science, like, you know, abstract kind of theoretical kind of person, I still don't really understand the uses for this yet. And the proofs are not trivial. The Rule 110 has a proof that's about 40 pages long, and it was proven by a student from U of I. And I think there was some kind of legal battle between Wolfram and him, but he did prove that it was Turing complete. And this is Conway's Game of Life, which they also prove is Turing complete. Here's some interesting things. They designed these flyers. They can fly around and carry information, and yet they're just running those simple rules. Isn't that cool? So that's one of the videos. You guys can just like, this is just stuff you can go, like there's so much you can learn online. It's ridiculous. You just got to know where to look. The Turing machine, it looks complicated. I don't know how someone really came up with this design, but there are people who do that. They come up. It kind of, here we go. What was it? This one. Let's double speed this. Look at this. So it's Conway's Game of Life, and it zooms out, and you'll notice that you got these generators here that are giving you like these pixel-like things that cancel each other out. You have a flyer, I think it's called, going around this box collecting information from the nearby boxes. Every cycle, see, there's the flyer, it goes around, collects information, and then it updates the generators. And you'll notice when you zoom out, you speed it out. If you just download this program called Golly, my laptop is just like this cheap, it's just a normal laptop. It can run something that fast because somebody designed a hash life algorithm that basically it'll start off slow. It'll be like generation 1, generation 2, generation 5, generation 1000, generation 1 times 10 to the 5th, generation 1 times 10 to the 20th. Like it's so crazy fast. It's like what? Like you'll just see stuff like really fast. Anyway, I just love that stuff. So that's about it. I'm not supposed to really talk to you guys too much all the way through to 2 o'clock. What'd you guys think of the class? Is it fun? Does anybody have questions about like the university or anything like that? From what I know? No? Okay. Yeah, they kind of mentioned to me like at the last second, hey, you might want, like, you guys might need to answer questions or something, so anyway. Thanks for participating. It was the first time I really taught a class kind of like that before, so any feedback would be awesome. Yeah. I don't want to be like monotone, you know, too much. I know things get boring.
Turing. What do you mean Turing? I didn't. Have a good rest of the day.
Thank you. You too.